here is an email regarding the makeup request for Lab 1. I said, hey, Dr. Mitchell, figure I need some more time. Could I make this up? I'll take the deduction here. Dr. Mitchell replied saying, approved per standard course policy. Your Lab 1 will be subjected to a standard 30% deduction. Thank you, Dr. Mitchell. And for the rest of the video, I'll be demonstrating my lab. Hi, my name is Arzate, and today I'll be demonstrating my makeup lab for multiplexers. To begin, we're going to look at our truth table right here, which will be useful to showing our Tinkercad as well as demonstrating our physical circuit. Here we see that we have our selector, our input A, and our input B. And based on the behavior on whether something is high or low will result in the output of Z for a 2-to-1 multiplexer. But taking a look here, we're just gonna sidetrack and look into our gates that allows us to operate a 2-to-1 multiplexer. Here we have an AND gate. If one of the inputs are 1, or if both inputs are 1, then the output would be 1. So we see here, if I were to switch this to 0, then we will also see an output of 0. Once again, if both inputs are 1, then the output would be 1, or 5 volts, or high. If we were to do a NOT gate, if we have 5 volts coming in, it'll result in 0 coming out. It's an inverted relationship. So if I were to put 0 volts coming in, we'll actually get a high of 5. For an OR gate, if we have at least one input being a high, then we'll get a high as an output. In this case, we have one input coming in as hot, so we get an output of 5. If we were to change this to 0, we see that nothing happens. If I were to change this down here to 5, again for an OR gate, if at least one of the values are 5 volts or a high, then the output should be a high as well, right? Based on the truth table and based on the AND, OR, and NOT gates, we can create a logic circuit here where we can verify using our truth table our multiplexer. And in this case, we have our selector, our input A, and our input B. In the situation where we have a high for input A and B, but a low for our selector, we will see that we will get a high as our output, and our schematic here can verify that for us. Okay. In the event that, let's say, our selector and A are high, but our B is low, then we should see our output being 0. So let's just go ahead and verify that. Yep. Again, if our selector and our A input are high, then we'll see an output of 0 as our, or low for our output. Looking at our multiplexer here, based on the 2-to-1 multiplexer provided, if we have 2 as our first stage and 1 as our second stage, and light up some LEDs using the schematic here, we can have a 4-to-1 multiplexer. Okay, taking a look here at our Tinkercad, we have our NOT, we have our OR, and we have our AND. And here is a representation on what I have here in front of me, where if this, in the case where we have our selector being high, and our A and B, A being yellow and B being blue, if they are both set to ground, then we should see that our output would be 0. and we see if we were to run the simulation, the LED is off. If you want to change that, we can go ahead and select the input A to be high, right? And our selector to be high as well. So right here, just looking at that, if we were to run this, then we see that the LED lights up. Okay. Looking here at our physical breadboard of our 2-to-1 multiplexer. Here right now I have my input A and B set to ground, so I can simulate what's on Tinkercad right in front of me. So if I want to have my selector to be high, I can put that to 5 volts. If I want to put my input A to high, I'll put that to 5 volts. And if I want to put my input B to 5 volts, that will result in our LED lighting up. And so that's our truth table following what's supposed to happen. If we were to run the case where we have our selector being 0, or to ground, but our input A and B, remember A being yellow, B blue is high, then it should remain high. Okay. If we were to have just our input A to be in power and input B in our selector to ground, then we will see that the LED is still on. Okay. If we were to just have our selector and our B to power, so I'm going to flip this. So selector A to ground, selector B to power, or sorry, B to power, selector to power. We'll see that that will turn on. Okay. Now, switching gears here, we can run a test where we can demonstrate our LEDs blinking, whether 10 Hertz or 0.5 Hertz. So I will connect my input A to 2, and I'll put my input B to pin 8, right? Actually, I will move my pin A to 4. Shifting gears to Arduino, we have the code needed to show when the LED is blinking at 0.5 Hertz or 10 Hertz, depending on the positioning of the selector. So right now, the selector is at ground, so that results in the signal be propagating the LED at 0.5 Hertz. Right here we have our for loop. We have a condition, so when we set our input A to high, it'll go through. If we set our input to low, and then the opposite is true. All right, going here, if we were to put our selector to 5 volts, we see that it starts blinking, so that means signal A starts to propagate, resulting in 10 Hertz. There you go. This concludes my lab 1. Thank you so much. Here is the email receipt showing my conversation with Dr. Mitchell, just giving me the green light to go ahead and do lab 8 during makeup week. Of course, my grade will be subjective to a 30% deduction. Here we have an LED, a 1000 resistor, potentiometers hooked up to the UA741 chip. For the demonstration of the comparator, we can see that as I start twisting the potentiometer, we see that it gets significantly brighter. And as I turn it back down, it gets dimmer, but it does not turn off. here's like a visual of what's happening here. If I were to go ahead and take an example here where my LED is very dim, not off, but if I were to increase it, eventually I will be able to roughly around half at 2.5 volts, but it does not turn off. Visually, we see here that our V out and our V plus stays at roughly 1.75 volts. As soon as I start turning it up, my potentiometer, it'll go together and it'll cap around 4.1, 4.2, whereas my potentiometer, I can twist it all the way to 5 volts. Just to demonstrate my code here, I'm bringing the inputs from what I would use for the op amp and connecting it to my Arduino from A0 to A3. And I'll go ahead, I'll read the reading that I'll get from my potentiometer, have it in columns in my serial monitor. And once I'm doing that, I can go ahead and bring it over to the processing side where I use the same structure that I used from, I believe it was Lab 4. I'm not too sure from the top of my head, but from another lab that we used to create the diagram here from 0 to 5 volts. I went ahead and added the extra legends to account for the extra pieces that we'll be using for this exercise. But yeah, I went ahead and commented out the data files that would save as like an Excel. Just wanted to keep the live data for the sake of this presentation. All right, thank you.